Okay, so talking about acids and bases, then I'd like to start with the definitions. You'll have two theories that they'll ask you to define in the test or in the exam, and this will remain the same when you get to grade 12. That is the Arrhenius theory. So these names are basically names of people who were chemists and who had a contribution to acids and bases, to the study of acids and bases. So one of them was Arrhenius, and then there's a team of two guys. One is called Lowry, the other one Bronsted. So that they combined those two names because they came up with the same idea and call it Lowry Bronsted. Okay, Arrhenius said that an acid is defined as a substance that will produce hydrogen ions or hydronium ions when it is dissolved in water. I'll show you what that means. So if I just make space here on top actually. So Arrhenius says that an acid will actually release H plus ions, or you can think of H plus ions. This is basically the same kind of ion or idea in acids and bases, or H3O plus ions in water. I'll explain why we can use either. So say for example you have an acid. I should have probably started this discussion with examples of acids and bases, but I'll open it up now. Let's say we have this acid HCl. That's an acid. So Arrhenius says that if I take this acid and put it in water, that means I'm reacting it with water, I'm going to get this. The H is going to be attached to the water, so this gives me H3O plus, and then the Cl is just going to be alone. So that's what happens when I take the hydrochloric acid and put it in water. I'm going to see that the hydronium ions are released. But what about the idea behind the H plus? That one is still the same kind of reaction, but this time around we don't really show the water as a reactant. We just show that the acid is passed through the water. Then you can just show water on top of the arrow, and then in the product side you show how the acid will actually dissociate. To dissociate is to break into ions. Then it's gonna be like that. So if you are actually I'll say this is preferred. This is the preferred method. If you are showing water as a reactant, then you have to show that the H plus is actually added to the H2O to make it H3O. Does that make sense?
Yes.
Yes. Then the Cl minus, from there, it's going to just be on its own. Then this one is really not preferred. I think you can use that at university when you are more comfortable with this. And that's basically Arrhenius. And then for a base, he says that a base is a substance that will produce hydroxide ions. So this one will release hydroxide ions in water. So if I take a base, for example, and I put it in water, let me make even more space. A good example of a base is NaOH. I take that and I put it in water. Water is H2O. Then what I'm going to have is actually the OH minus, and then for a base we can just show the ions because some of these things are just going to be spectators, and the Na plus on its own. So probably for this one we can just show that water was used to dissociate this. I can just put it on top like that so that I can see the ions in action. But every time we talk of a base, what you'll see is you'll see these ions OH minus produced. They'll actually show them in the questions. So then that is based on Arrhenius. Bronsted and Lowry, their definition is very simple and straightforward, and they actually like those ones. Sometimes it's called Bronsted Lowry or Lowry Bronsted. They say that an acid will actually donate a proton. So an acid is a proton donor, and by a proton we mean the H plus ion. Proton donor, and then a base is simply a proton acceptor. The proton is still the H plus acceptor. So it's a matter of being comfortable with the definition. Arrhenius, a base will release OH minus, an acid will release H3O plus. Those are different, but for Lowry Bronsted, an acid will donate H plus. A base will take that H plus from the acid. So an example of that, let's say we have this acid-base reaction. And what we're gonna have at the end of the day is going to be, no, I don't want actually a neutralization. I'll just use this first example that I have. You can see HCl, which is an acid, is reacting with water to produce these products, and you can definitely say that HCl has donated its H. At the end of the day, on the product side, it's now missing an H. So that's how we know it has donated the H. Where did it donate the H? It's actually donated the H to the water. Then the water accepted that H to become H3O plus. So we call the water a base in this case. Let me go through this and see what else we have. Okay, this is very important. We call an acid that is, okay, before this, let me actually go and show you the examples. I think this note should have, oh, there is examples. Yeah, there is examples right here. Okay, so let's first look at that. Common strong acids. You can see strong acids are these ones right here. So common strong acids include hydrochloric acid, which is HCl, nitric acid, HNO3, sulfuric acid, H2SO4. Those are the most common and the ones that you really expect to see in the exam. There's also, now let me just stick with those that we have there. And then common weak acids are this here. So there's oxalic acid, which has this formula into COOH, all 2. And then there's hydrofluoric acid, which is just HF. There's sulfurous acid. Some of this you'll not really see in the test. Let me highlight those that are really expected. There's ethanoic acid. This one is most common. There's phosphoric acid. This one they can have in the test. And oxalic acid as well. I've seen it quite a lot. And then for the bases, most common strong bases, NaOH. This one is like always there in the test. They really like that one. So that's a strong base. And then you have potassium hydroxide, also an example of a strong base. Not usually that I say it, but sometimes if they are not using NaOH, they'll use KOH. Then example of weak bases, you have sodium hydrogen carbonate. This one they really like. The formula is NaHCO3. And you also have calcium carbonate. This one they really like as well. CaCO3. Sodium carbonate, I've seen it a number of times. So I'll say this one as well, they do like here. And also ammonia, the last one, they really also like that one. So those are examples of weak bases. So let's now discuss what is meant by monoprotic, diprotic, and triprotic acids. A monoprotic, the word mono on this side of the screen, the word mono means one, and then the word di means two, the word tri means three, and the word protic means a proton. So a monoprotic will donate one proton. A diprotic will donate two protons. It's going to do that in two steps. This is the first step. This is the second step. A triprotic will donate three protons, and this one will do that in three steps. In the first step, it's going to donate just one proton. In the second step, it's going to donate a second proton. You can see, if you are able to see this, it starts as H3PO4. It donates one proton to become H2PO4. Then you see a minus there to say, because we lost the proton, which is positively charged, then our net charge is going to be negative. Then for step 2, we're going to take that H2PO4 minus and start with it. That's going to lose another proton to become HPO4. Now we lost another positive, so we get 2 minus as our ion. Then that is the lost proton. Then we take that HPO4 2 minus, we start with it again, and we lose the final proton to become just PO4 3 minus. And this is the lost proton. So all in all, we're going to lose 3 of them. Okay, does that make sense?
Yes.
Okay, cool. Then we also have what we call conjugate acid-base pairs. This is very easy. I'll just use an example. So let's look at this example here. They will say identify the conjugate acid-base pairs in each of in the following example. Then they have this acid, nitric acid, reacting with water, and we have the products. The product is the nitrate ions and the hydronium ions. And because it releases hydronium ion in solution, you can definitely see that it is an acid. So what HNO3 is going to do, it's going to donate a proton to water for water to become H3O plus. So because HNO3 donates a proton, we can say that this thing is an acid. Why? Because it donates a proton. Donated a proton. Then you go on the product side. Which one on the product side looks like HNO3? That's going to be it's going to be NO3. So you do that arrow there, and then you say that thing that you have on the other side is a conjugate base. If you start with an acid, on the other side you have a conjugate base. Then the water is accepting a proton to become H3O plus. So you take a line, you show that water becomes H3O plus, and then because water accepted a proton, it's now a base, and on the other side we call that a conjugate acid. That's all there is to it. Let's look at another example. For example, if we look at ammonia here, we're gonna have NH3 on the reactant side, and on the product side we see something that looks like ammonia is NH4 plus. So those are conjugate definitely. Then we first check, does ammonia gain or donate a proton?
Gains.
It donates, right? It gains, it accepts a proton, so we call it a base. Then on the other side, that is going to be automatically a conjugate acid. Conjugate acid. And then water is going to lose a proton, so it's going to donate a proton, so we call it an acid. And something that looks like water is OH minus on the other side, so that thing is called a conjugate base. So the conjugates, what they mean is that, remember the forward reaction is like this from our study of energy and change. This is the forward, the reverse is going in this direction. And because our reaction is reversible, you can see with the double arrow there, it means we can go from products to the reactants. And if you go in that direction, you can see that OH is becoming water by accepting a proton. That's why we call it a conjugate base, because in the reverse, it's going to accept a proton. Then if you look at ammonium ion, it starts with NH4 plus. At the end of the day, it ends up as ammonia, NH3. So it's going to lose a proton, or it's going to donate a proton. That's why we call it a conjugate acid, because in the reverse direction, it is really an acid. Okay, that's important to realize. Then another very important definition in acids and bases is an ampholyte. This one is like always there in the test. It's not an acid-base question if you don't have an ampholyte definition in there. So how do we define ampholyte? An ampholyte is a substance that can act as either an acid or a base. Simple as that. So in one reaction, it's going to act as a base. But if we try another reaction, we see that this thing actually acts as an acid in this reaction. So it doesn't really have an identity. It doesn't fall into common acids and bases, because these ones don't change. They are not ampholytes. They are really acids or bases. But there are some of these things that are really going to change around, and they are called ampholytes. So let's look at examples here. If you look at HSO4 minus, if I put this thing in water, it's going to become, okay, on one of the days, it's going to become H2SO4 plus OH minus. On one of the good days, if you react it in water, it's going to decide to become SO4 minus plus H3O plus. So let's look at those two equations. We can see that in the first equation, its conjugate is H2SO4. So it looks like it accepts a proton. Is that correct?
Yes.
Yes. So it's going to accept a proton. This means it's a base. Then the water itself is going to donate that proton. So the water is an acid, and we can match it with its conjugate. So this means this guy is a conjugate acid. This guy is a conjugate base. Okay. Let me move this reverse sign to the other side. And you can see also the reverse works. H2SO4, you can remember that from the strong acids, this one will always be an acid. So conjugate acid is correct. So let's look at the second equation. We see that HSO4 minus now becomes it becomes SO4 minus. So it definitely donates its last proton. So because it donates, it's an acid. And this other thing that it becomes is a conjugate base. And H2SO4 will accept that proton, so it is a base. And the thing that it becomes is a conjugate acid. Conjugate acid. then when you check back, you see that this guy acted as a base in the first reaction. Now it acted as an acid in the second reaction. So that's what we call an ampholyte. Okay, it can act as both acid or base. Okay. Then other important information. In everything in this study guide, I do believe it's important, unless if there's any other information that is missing. So if we look at concentrated and dilute acids and bases, let's see what they say. Concentration is the number of moles of solute per unit volume of solution. We did this in stoichiometry. We also know the equations for concentration, it's those two. And then they say a concentrated acid or base contains a large amount of moles of an acid or base in relation to the volume of water. So if I say this acid is concentrated, it means I have more of the acid, which is the solute, than the water, which is the solvent. So we call that more concentrated. Remember, we said that concentration is, we can think of concentration as the taste. So if there's more of the sugar than the water, we say this tea is sweeter. If there's less of the sugar compared to the water, then we can say this tea, I say it's less sweet, or it's dilute. And then we can say a dilute acid or base will contain a small amount of moles of the acid or the base in relation or in comparison with the volume of the water. I think that's pretty straightforward. So an example, a concentrated strong acid has 1 mole per decimeter cubed of water. A weak acid, we can say it still has 1 mole per cubic decimeter. It all depends on what is the amount of solute we used versus the volume of solvent, which is water. Then how do you identify something that is dilute? It's going to have a small number of concentration. So we can see the same example. And as I think they don't include the dilution and concentration equation, which I'll show right here. So dilution. Let's say we start at state 1 here, whereby we put this amount of acid in, and the volume of this acid is 2 decimeter cubed, and the concentration of this acid is 1 mole per decimeter cubed. Then what I'm gonna do to it is I'm gonna add water. Let's say add more water. Then if I do that, I'm gonna have a mixture, but I'll just show it separate like this. But it is a mixture now, and the water is like up to this point. So at this point, state number 2, we know that definitely the taste is no longer going to be the same. If this was sugar, it's no longer going to be sweeter because we added more water. So in other words, we diluted it. So how can we find the new concentration or the new taste? We have to be given the volume for us to identify that. Let's say they added 5 decimeter cubed of water. Then what is the new concentration? This means V2 will be the initial volume of the acid was 2. We added 5 more volumes, so then the new volume is 7 decimeter cubed. To find the concentration, we're going to use this simple equation. C1 V1 is equal to C2 V2. I think we might have touched on this a little bit on acids and bases, but the idea behind that is that the number of moles of the acid in the first beaker is still the same as the number of moles of the acid in the second beaker. Why? Because I'm not adding or removing acid. The only thing I'm doing is I'm introducing more dilute water, which doesn't add in any way to the number of moles of the acid. So number of moles 1, if it was 1 mole, the number of moles 2 is still going to be 1 mole. And we know that we have this equation, concentration is number of moles over volume. So if I write this in the form of number of moles, is concentration times volume. And if N1 is equal to N2, then that's how we formulate this equation. It means C1V1 is C2V2. Okay, but this one, I think it is given in the formula sheet. It's going to help you to identify the new concentration after the diluting. Okay, is that fine, or do you have any questions so far?
No questions.
Okay, then strong versus weak acids. Yeah, this is very important, especially in grade 11. The strength of an acid or base refers to the ability of the substance to ionize or dissociate. Very important. So let me also talk about it on the side. Strong acid or base, weak acid or base. So we say that a strong acid or base will ionize or dissociate. This just means it's going to break into its ions completely and very fast. And then if it's weak acid or base, it's going to ionize or dissociate incompletely or very slow. Okay, so let's say we have an example. We just put a strong acid in a beaker or a weak acid in the same beaker for the second example. Let me actually make this look like a beaker. Okay, so we add the acid or the base that is strong in water. What we're gonna see is that instead of having, let's say this was HCl, if I add it in water, I'll then call it aqueous. In the presence of water, you remember probably from our discussion is that it's going to dissociate. So if I zoom into the molecules here in the beaker, I'm not going to see HCl. I'm going to see H plus, but remember I don't like to use H plus for this. I'll see H3O plus in there, and then I'll also see Cl minus in there. So it's going to break down into the ions, and then if I do the same on this other side, but now it's weak, I'll show you what I'm going to see. I still have HCl aqueous. No, sorry. It should be a weak acid. Which one can I pick? Let me pick CH3 COOH aqueous. What I'm gonna see in that, it's going to be H3O plus ions and CH3COO minus ions, because it's when it loses an H, it's going to attach to water to become H3O plus. Then when I lose the H on this, I just become CH3COO, and I have to take care of the missing H by the negative. But most importantly, I'm also going to see CH3 COOH. So it also remains the same. While some of it break down, some of it still remains the same. That's why we call it that it's dissociating incompletely, to say it doesn't really break down into ions, all of it. Some of it is not going to break into ions. And that's the idea behind a weak and a strong acid. The bases will still behave the same. If it's strong base, it's going to dissociate completely. If it's a weak base, then some of the original base is going to be remaining in the water as well. That makes sense, right?
Yes.
Okay, cool. Then we can see a couple of examples here. We show this reversible for weak, because while we can make products, we can also come back from products to reactants to form the main thing. That's why we use reversible. So let me also note it down here. If it's a strong, we use one arrow, forward arrow only, forward arrow. When it's weak, we use a reversible arrow. Reversible. This means we can form products and we can form reactants. Okay, that's quite important, because sometimes they'll test you, they'll say, show us how COOH into 2 dissociates. And if you forget that it's a weak acid, then you might use one forward arrow, which will be wrong. You have to use a double arrow or reversible arrow to show that it's gonna ionize incompletely. Okay, the next thing to talk about, this I've seen this in the grade 12 question papers actually, so it's very important as well to understand reaction rate. Reaction rate increases as the strength of the acid or base increases. I already mentioned that a strong acid will ionize faster. So strong acid reacts faster or ionize faster. Strong ionize faster. And if the concentration as well is high, then we can have faster reactions. So I think that's also quite intuitive. If we have high concentration, then we're going to have fast reaction. And then when it comes to conductivity, this is basically how well something will conduct electricity. So let's say we have a battery. This is a battery, positive and negative. And I take that battery and connect a light bulb on the other side. So this is my light bulb. I connect a light bulb on the other side, but instead of actually connecting it with the other wire, I'm going to take that wire and pass it through a solution of an acid or a base. I'll use an acid, H2SO4 aqueous. Then I take that wire from the other side of the battery, I drop it in the solution. I take another wire, I continue the connection. Then we say that if this acid is strong, then the ions inside, remember there's going to be only ions in there, H3O plus and SO4 minus, 2 minus. The ions are going to carry electrons from this missing wire to the other. So at the end of the day, we're going to have this light bright, because there's ions which have been broken down from the acid or base that will cause the electricity to continue moving even though the wire is disconnected. But if I put a weak acid in there, then it's going to be really difficult for the electrons to move. So at the end of the day, the light will burn really dim, because the base that I have or the acid that I have is weak and it dissociates or ionizes incompletely. So, in other words, conductivity is going to increase, or we're going to have a bright light if the acid is strong or the base is strong. And conductivity is going to be low if the acid or the base is weak. We can even increase the concentration of the acid in order to make the light burn even brighter. You can actually watch some experiments on this. If I actually add more and more acid and then I stir in the beaker, the light will burn brighter because now we have even more ions that are carrying the electrons from point A to point B. Okay, does this also make sense?
Yes.
Okay, cool. Then I think I'll say at the end I should talk about the questions that you had, but the pH is also a very important concept. It's gonna be there in grade 12, and in grade 12 it's really advanced. But for grade 11 I don't think it's that tough, and I'll just leave this for Monday because we have to do some calculations, I believe, or some more theory on that. So this is really too summarized for us. Okay, but they are indicators for pH, so we'll also continue with that on Monday. But for today I want us to talk about acid reactions. So we say that let me make this smaller. We say that acid reactions are reactions during which protons are transferred, and obviously we know that an acid will always donate this proton. It's never going to accept it. Okay, let's look at an acid reacting with a metal. I'll highlight this with different colors just so that you can identify them. Let me actually erase that. An acid reacting with a metal. We already know what an acid looks like. Now we have to understand what a metal looks like. On your periodic table, you have a list of, they actually show you in your textbook that this part of the periodic table is metals, stuff like that. So if you have a metal, say for example Mg, that's a metal, or copper, that's also a metal, and you react that with an acid, what kind of products do we expect to have? So let's see. There is an acid and we use Na for a metal. The kind of products that we expect to have is actually a salt, a metal salt, plus hydrogen gas. I'll get good notes on this because they don't really say in words the products. Okay, sometimes they do. Yeah, they do show them. Actually, it's salt and hydrogen gas. If it's an acid and a metal, then let's go to the next one. I'll highlight this in purple. If we have an acid with a metal hydroxide, the question is, what is a metal hydroxide? A metal hydroxide is taking this metal and then putting hydroxide on it. It's going to look like that. So that is a metal hydroxide. What is the product if I take that kind of reactant and react it with acid? So let's see, it's going to be salt and water. There's the acid, there's the metal hydroxide. The product is always a salt hydroxide. So it's basically, if I just show it here, H2SO4 plus MgOH2 going to have Mg is going to take these ions So MgSO4 plus H2O. The other thing is water. Okay, so at the end of the day, you see that the Mg has just taken the SO4 ions from the HSO4. Why? Because HSO4 in solution, if it's aqueous, and that's always the case, then it's basically just two H pluses, or you can think of this as two H3O pluses and SO4 minus, 2 minus, that is just floating around. And then Mg comes around, and Mg has these ions, Mg2 plus, which is gonna attract this, and then it also have these ions, OH minus, which is going to take this one. You should probably notice that in fact this metal hydroxide is a base. Think a strong base as well. So in solution, that's why it's gonna release OH minus. H2SO4 is an acid, so in solution it's gonna release H3O plus. The products at the end are just swapping around so that we have a salt and water. That's always the case. Most of these are really simple. Like, we are closing off now. Let me highlight the next one. An acid and a metal oxide. A metal oxide means a metal with the oxide ion. Like, take Mg again. Mg is this. Then Mg ions is Mg2 plus. Oxide ions are 2 minus. So if we match these two, they become MgO. So that's a metal oxide. If I take an acid and react with that metal oxide, what I'm gonna have is a salt and also water. So it looks similar to when I have a metal hydroxide. So I take H2SO4, I react with MgO. You still have to balance this as well, but just show the product. Mg is going to steal SO4 again, and we're gonna have the other things making just water. So if I were to balance this, I'll first choose the simplest. This Mg looks like Mg is balanced. Then the next simplest is S, which is balanced. Then I think the only thing I need to balance is oxygen. Oh, it's actually balanced. It's 5 and 5. Yeah, everything is balanced actually. But what you notice is that an acid plus a metal oxide gives you a salt. That's a salt and water. That's always the case. It doesn't matter what kind of metal oxide you use. It's always going to be that metal salt and water. Let's see the last thing here. The last thing, very important. This one is the one that always trips people. Why? Because it is complicated. The products are complicated. Very trippy, this one. I remember it tripped me in my first test of chemistry for university. So you gotta be very careful with it. We have an acid and a metal carbonate. Let's look at what that means. Acid plus metal carbonate. Okay, are you still with me?
Yes.
Okay, so I'll use the same acid, H2SO4, and then I add a metal carbonate. I'll use Mg as my metal. Carbonate ions are CO3 ions. Then the product is going to be a salt. So Mg, okay, let me actually show how this breaks down. They are all aqueous solutions. This one is going to break into H3O plus and SO4 2 minus. MgCO3 is gonna break into Mg 2 plus, and CO3 2 minus. Then Mg is gonna match with that. So we're gonna have Mg SO4, that's our salt, very standard, plus water is gonna be there, but now we add another product, carbon dioxide. That is resulting from the fact that we now have C there. So we're gonna have carbon dioxide as one of our products. So still we get salt and water, but most importantly, the other product is carbon dioxide. And it doesn't matter what kind of metal carbonate you use, carbon dioxide is always going to be there. Carbon dioxide, okay, like that. So that is it for the reactions that you need to learn for acids and salts, or acids and metal oxide or whatever. I think they are missing acid and base, but it is the same. When you get to what we call titration, you are basically having what we call a neutralization reaction. Neutralization reaction. In other words, you have an acid-base reaction, acid plus base. So let's take H2SO4 and react it with NaOH. One arrow, because that's neutralization and it's two strong acids. Two strong substances, strong acid and strong base. Strong acid, and this is a strong base. But once again, what's going to happen is that the acid is going to break into H3O plus and SO4 2 minus in the water, because it's aqueous. And this one is going to break into Na plus and OH minus in water. Then our products, this one and this one, are going to match, positive and negative, to become a salt. So Na2SO4. That's how my salt is going to look like. Plus, when remember, you can think of this thing as H plus. So when H plus and this react, or H3O plus and this react, it just becomes water. So more and more water, H2O, that's water. And that's basically it for the reactions. So I'll say let's take like 2 minutes to see what the answers are gonna look like on your homework. Write down the salts that form from the following reactions. 1.1, lithium hydroxide. Lithium hydroxide, lithium is a metal, hydroxide is OH, so you're gonna have lithium OH plus acetic acid. So acetic acid is actually this, CH3COOH. Gonna use acetic acid a lot in grade 12. And then I can ask a question, is acetic acid a diprotic, a monoprotic, or triprotic, or even tetraprotic acid? In other words, how many protons do you think acetic acid is going to donate?
It's triprotic.
Okay, you think it's tri. Okay. This is called, in grade 12, you're going to do this. It's called an organic acid. What it's going to do is that it's going to be stingy with these H's that are inside the molecule, and it can only donate this one at the end. Does that make sense?
Yes.
Yes, so at the end of the day, this thing is a monoprotic. acid. It's only going to donate one. And the products are going to look like this. You can also do the breaking down thing. Lithium is going to break down into lithium plus and OH minus, and then the acid is going to break into CH3COO minus and H plus or H3O plus. Then the products are going to be, the negative and the positive are going to attract, so you're going to have CH3COO lithium plus water when I mix H plus and OH minus. That makes sense, right?
Yes.
Yes, so let's quickly fill these other ones. Magnesium hydroxide. Magnesium is Mg2 plus, and when it meets hydroxide, hydroxide is OH minus, so it means, I think this is pretty basic from grade 10. OH minus, I need two of them in order to balance the 2 plus. So that's why I'm going to have Mg into OH2. And I add sulfuric acid. We already did an example on this, so it's going to become MgSO4 plus water. And that's it. That the reaction, oh wait, let's see if the reaction is balanced actually. We have that the OHs, they are not balanced. What do we need to balance it? But the thing that is unbalanced is the water. So I need to multiply water by something.
2.
2, correct. So I needed 2 there to balance it. There we go. The lithium one was balanced already. Let's look at beryllium oxide. Beryllium is a metal. So Be, oxide is oxygen. I think beryllium is 2 plus, if I'm not mistaken. So beryllium oxide will be BeO, like this. I could be wrong about the beryllium because beryllium is not really used a lot, so it's not one thing that I crammed. Hydrochloric acid looks like this. So the products are going to be beryllium chloride, right? Because chlorine is Cl minus, then I'm gonna need 2 of that plus water. Why? Because no, wait. Yeah, that's correct. Let's go back to metal oxide and see that indeed we are doing the correct thing. Yes, metal oxide will also have water. The only thing that will not have water, that will have hydrogen gas, is just a straight up metal. So that one is right. And if I have to balance, it means I'm gonna need a 2 right before HCl. And you can verify that indeed it is balanced. So let me pull this a little bit to the side quickly. 2. Okay. Sodium oxide is also a metal oxide, and sodium is Na plus. Oxygen is O2, so I need 2 in order to balance the oxygen. Then this is plus. Nitric acid is HNO3. So the products are going to look like this. Actually, do you want to try to give me the products?
Try.
Yes.
Can I quickly do it first?
All right, yeah, you can do it at first. You can do the breaking down in aqueous solution, and then you can also show how they are going to swap around, basically just swapping ions.
Is it Na2NO3 minus plus H2O? So I can't hear you.
Okay, I'm sorry. I muted when I was waiting for you to actually do the question. Okay, I apologize for that. Also in the recording it's gonna be muted, but I'll just quickly say that again. You can see that the Na, it's just Na plus. From the periodic table, you can see that Na just have a plus, no 2, no 3, but oxygen have a 2 minus. So to make Na2O, I need 2 Na pluses and 1 O2 minus. And then for HNO3, H is H plus. That one is like the very first element on the periodic table, and it's gonna have a plus. So if I only need just NO3, it means NO3 ions will have just 1 minus. So now I need to combine Na plus and NO3 minus, so they become NaNO3. No 2 in between. Does that make sense why we don't have 2 there?
Yes.
Yes. Therefore, the other thing is going to be water, and then what's remaining now is the balancing. So I put a 2 there to balance the NO3. So I also put, no, that 2 there was to balance the Na. Then I'll put a 2 there again to balance the NO3. So I think balancing though is quite straightforward. So I trust that one is good on your side. So just make sure that the ions are correctly represented. Let's look at potassium carbonate. What will be the formula for potassium carbonate? Think about it.
Is it K2PO4 minus?
No. Carbonate ions are CO3 2 minus. That's it. That's a clue.
Okay, 2CO4 minus.
P, did you say P2?
K2CO4
K2.
minus.
All right, yes. Potassium is K, so potassium carbonate. We know that potassium ions are K plus. So we need 2 of the Ks, K2CO3, in order to balance the 2 minus on the C. So that's a metal carbonate. Do you remember the metal carbonate?
Yes.
Yes, we put sulfuric acid on that. And what are the products? Do you remember the products for metal carbonate plus acid?
It's gonna be salt, water, and carbon dioxide.
Good. Then what kind of salt do we have? We can do a quick breakdown. Let me show it here. K2CO3 plus H2SO4. So if I just break this down, I'm going to have, this is, remember, if you know one of the ions, then it's going to help you to know the other one. This is CO3, 2 minus. You did ions basically in grade 10. This is K plus and K plus. Then if I break down the acid, this is just H plus and H plus. Also with SO4, 2 minus. So the two Ks are going to be paired with this one. I think I should use a red line for that. And the other things are going to become water and carbon dioxide. So these ones are going to become K2SO4. Positive and negative are going to attract, and we know that there's a swapping of ions. So the salt itself is K2SO4 plus water plus carbon dioxide. Okay, do you think you could have been able to do it on your own?
Sure.
Okay, let's look at the last one. Copper oxide, copper 2 oxide. How does copper 2 oxide look like?
CuO.
CuO, that's correct. Why? Because if I say it's copper 2, it means it's copper with a 2 plus. The reason why we have to specify is because we also have a copper that looks like this, copper plus, and that one will be copper 1O, or it's gonna look like this basically. If I put it in oxygen, it's gonna look like this, copper 2O. That's copper 1 oxide. So the 2 basically explains this 2 plus here. Then because oxygen is also O2 minus, they are going to match perfectly to become copper O. Plus sulfuric acid. What are the products? What did you get for the products of this one?
I'm still calculating.
Okay. All right. Remember, it's just the swapping around of ions, and then you can remember that if it's copper oxide, it's a metal oxide and acid. What will be the products? It's always going to be salt and water. So the thing to figure out is basically the salt, but you find that by swapping the ions.
CuSO4
CuSO4, yes,
plus H2O.
correct. So that's already also balanced, so straightforward. Let's do question number 2.1 quickly. Complete and balance the following reaction: Ag2CO3 plus HNO3. What will be the products?
And AgNO3 plus H2O.
AgNO3 plus H2O. Is that it? Here's the clue.
Plus carbon dioxide.
Plus carbon dioxide. There we go. So you'll see if you miss carbon dioxide, you'll see that, oh, there's actually a carbon there, which I don't really have in the products. So I remember that, oh, it's a metal carbonate. A metal carbonate and an acid will give me a salt, water, and very importantly, carbon dioxide. Okay, now we can look at balancing. Let's see if, yeah, there is definitely some balancing to do because Ag is not balanced. So I'll put a 2 there to balance Ag. And then that will unbalance the NO3. So it means I have to put a 2 there on NO3. Then let's see if that balances it. And yes, it does balance it. Can you see that? The H's are 2 and 2 on the other side. And the NO3 are 2 and 2.
Yes.
All right. Perfect. Then yeah, we'll stop here for acids and bases, and then on Monday we'll just continue with the discussion. Or because Kia won't have time to watch the recording. But anyways, I'll see what to do on Monday. But we still have a little bit more to do on acids and bases before we say we are done with it. Okay. Then yeah, we have reached the end. Yes, do you have any other question or do we close?
I don't have any other questions.
Okay, all right, thank you. Do more questions. I feel like I see that this last question was only 2.1, so you can also try 2.2 and so on in your book, and then see if you get the correct answers and also the balancing. If anything doesn't balance correctly, try to figure out where the mistake is, and if you can't figure out where the mistake is, you can always come and ask me in the group. But I'll say just to close, everything else will produce a salt and water, including acid and base. The only difference, salt and water including acid plus base, the only difference is when you have just a straight metal, that will produce hydrogen gas because there's no oxygen anywhere right there in the metal. But also another exception is when you have a metal carbonate. Whenever you see CO3, think CO2 as the product. Okay, is that fine?
Yes.
All right, thank you. I'll see you on Monday.
Bye.
Bye-bye.